So we're looking at this problem number 12 from the Newton's second law packet. What we have, all pulleys are perfect, surface is frictionless. If the mass M1 is equal to M3 is equal to 10 kilograms, M2 is equal to 5 kilograms, and use G equal to 10, find A1, A2, and A3. So look what's going on here. We've got a basic like mass with a rope connected to a pulley, but then on the pulley this is sometimes referred to as an Atwood machine. You've got a mass and another mass, right? This one is accelerating at A2, this one's accelerating at A3, and this one's accelerating at A1. Okay. Does the situation make sense to you guys? I'll give you a chance to like look at it and take it in. I'm also going to tell you one other thing before we get started here, which is that this, oh no. Can I get a white color? Will they let me do white? Yep. Draw white. This is not the direction of the acceleration of this object. It's the direction of the acceleration relative to, it's actually going to accelerate the other direction. And I'll talk about that in a second. This one is actually going this way. They're both going to be going down. I can prove it to you guys if we need to. There's even videos of this kind of system online. Not exactly this one, but a similar one that we'll look at here in a second. Okay, so how do we handle the scenarios of what's going on here? So we've got 3 different accelerations, right? And I'm going to make a couple comments here. First of all, that acceleration, okay, why won't it let me do that? Okay, so if we look at the system, A1 is moving to the right. The pulley is going to be moving down, right? So I'm going to say that the acceleration of the pulley is going to be down like this. But I'm also going to make a statement here that each of these accelerations are relative to something. Just like velocities are relative, accelerations are relative as well. Okay? So what I'm going to say is that this acceleration, A1, is actually we're going to call it A1e. That's going to be equal to the acceleration of block 1 relative to, what do you think I picked E for? What does E represent? What do you guys think? Yeah. Okay. And so this is also A1e. Okay. In a way, also, this is equal to the acceleration of the pulley as well, but we'll get to that in a second. A2 and A3. Now, what do these represent? Well, there's 3 different things we can write down here. First of all, we could write down, this is going to be, we're going to call this the pulley here. This is going to be P. I would say that the acceleration of the pulley relative to the Earth is also going to be equal to the acceleration of block 1 relative to the Earth. Does that seem reasonable to you guys? And then I'm going to make this statement. I'm going to say the acceleration of block 2 relative to the pulley should in some way be related to the acceleration of block 3 relative to the pulley. And the reason for that is that as the pulley descends downwards, M2 is either going to move up or down depending on its mass. But we look at the masses and we realize that this one's 5, right? And this one's 10, right? So all things being equal, if we completely remove the upper half of the problem right here, and we just think about what would happen if this was a fixed, if there was a fixed point right here, and you had these, what direction would M3 go relative to the pulley? Would it go closer to the pulley? It would go down, right? And this one would go up, right? And if this one went down by 1 meter, how far would this one go up relative to the pulley? Does everyone agree with that? That however far this one goes down, this one goes up the same distance relative to the pulley. Not relative to the ground, relative to the pulley. Is everyone on board with that? Does anyone have any questions about that? So, no, I'm saying like you take a pulley, you've got a mass over here, you've got a mass over here, right? And you make it so that this is 10, and you make it so that this one's 5, and you suspend the entire thing from a ceiling, then if this one moves down by some distance, like let's say 1 meter, this one has to move up by exactly the same distance, because they're all connected by only one rope. There's no double pulley system here, right? I know we just did 2 problems where one thing went down a meter and the other thing only moved half a meter or something like that, but in this situation, at least relative to the pulley, the distance this one moves is the same that one goes up. Right? Correct. That's right, exactly. So then what we have then is A2 pulley and A3 pulley. How are these related to each other then? I had an equal sign, but they're actually not equal. How are they related to each other? One person say it. What is it? Exactly, like that, right? A2 pulley is going to be equal to the negative of A3 pulley. Everybody agree with that? Now, what I mean by each of these here, okay, this is actually going to be A2E. That's going to be down. And this one is going to be A3E right here. Okay, both of those will be down. Okay, but maybe you can figure it out. I don't know if you can or not. If I know this relationship, and I want to figure out, for example, what is A2E equal to? What is it equal to? Think about our relative velocity equation. What would this be equal to in general? You've got 3 objects, right? The 3 objects are 2, pulley, and earth, right? Which one's missing here? The pulley, right? So do you guys, this is how you do it. You go 2, and then the third thing, pulley, and you put you put pulley here, and you put the other one you need. So the 2 is this one, and then E shows up at the end, and there's your equation. That's your relative acceleration equation, right? Does that one make sense to you guys? The next equation then is going to be for A3E, right? And I maybe take a second to write it down yourself to see if you understand. Write for yourself what this one is going to be. It's going to be exactly like this one. So it's just take a second. Write down what this one's going to be. What's the first term going to be? Everyone got it? Does it make sense? So we've got these equations. We got this one, we got this one, we got these guys, right? And what I want to do now, actually, let's erase this line. What I want to do now is I want to add all our equations together and substitute to get a simple relationship. So I want to take this equation, and I want to add them together like this. And I want to replace APE with A1E. So here's what we're going to get. A2E plus A3E is equal to A2P plus A3P is equal to 0, right? And then 2 times this. And then I'll replace this one. Our final result is A2E plus A3E is equal to 2 times a pulley and earth. These were the same, right? This is how we tie everything back to this guy. This becomes A1E. And then in terms of the symbols in the problem, it's basically just A2 plus A3 equal to. Now that are all in the same reference frame, we don't need to keep writing the subscript anymore. We can just do that. And that's your result. You'll see this result proved in many different ways on the internet if you want to. This is often referred to as a double Atwood system. It's not exactly a double Atwood system, but in terms of the way the accelerations are related to each other, this is how it's going to be in a lot of problems like this. The sum of the bottom 2 accelerations is equal to double or 2 times the acceleration of this guy right here. And it's possible I could find you there's a really nice video of a system like this. So if we go to double Atwood machine, see if I can find the video I want to find. I'm going to go ahead and stop streaming right here because